Elastic and inelastic collisions. Momentum is conserved in all collisions. Total energy of the system is conserved in all collisions. In a perfectly elastic collision, kinetic energy is conserved. So we can say that the kinetic energy before the collision will be equal to the kinetic energy after the collision. So we have half times the mass of body 1 times the initial speed of body 1 squared, plus half the mass of body 2 times the initial speed of body 2 squared, will equal half the mass of body 1 times the final speed of body 1 squared, plus half the mass of body 2 times the final speed of body 2 squared. This would require no sound produced in the collision and no heat energy produced. The only truly perfectly elastic collisions would be between atoms and molecules. However, some macroscopic situations can come close. Colliding snooker balls come close to perfectly elastic collisions. If a moving object has a perfectly elastic collision with a stationary object of equal mass, the moving object is stopped and the stationary object moves off with the same speed as the moving object had before the collision. So here we have the red ball moving towards the blue ball of equal mass. The red ball stops and the blue ball moves off with the same speed and therefore the same kinetic energy as the red ball had to start with. If the two objects of equal mass move towards each other at equal speed, they will return along the path they came along and with the same speed as before. So here we have the red and blue ball moving towards each other, they collide and move off. In a perfectly inelastic collision, the two objects will stay connected after the collision. Some kinetic energy remains, but the loss of kinetic energy is a maximum. So here the red object approaches, collides and attaches to the blue object and they move off together. This is an example of a perfectly inelastic collision. If a lump of soft dough was dropped onto the floor, the momentum of the dough would be passed to the dough and earth, which are now connected. Clearly the increased movement of the earth would be absolutely negligible, so effectively in this extreme case all the kinetic energy has become heat and sound. Most collisions would be somewhere between the perfectly elastic and perfectly inelastic examples we've covered. Most collisions would be therefore partly inelastic, but we only need to call them inelastic collisions. Let's look at an example. A trolley of mass 2.4 kilograms travelling at 0.6 meters per second collides with a trolley of mass 1.2 kilograms travelling in the same direction with a speed of 0.09 meters per second. The heavier trolley has a speed of 0.26 meters per second after the collision. Find the speed of the lighter trolley after the collision. Well, for this we can use conservation of linear momentum. So the momentum of the two objects before will equal the momentum of the two objects after. We want to find the speed of object 2. So we can rearrange to get this expression. Putting in the numbers gives a speed of the lighter object of 0.77 meters per second. Is this collision elastic or inelastic? Well, if elastic, the kinetic energy is conserved, so we'll find that the kinetic energy before the collision equals that after the collision. We can find the kinetic energy before the collision as half times the mass of object 1 times the speed of object 1 squared, plus the same for object 2, gives us half times 2.4 times 0.6 squared, plus half times 1.2 times 0.09 squared, an initial kinetic energy of 0.44 joules. The final kinetic energy, given by this expression, is again 0.44 joules. So in this case the collision is elastic. In a different collision, the 2.4 kilogram trolley travelling at 0.6 meters per second collides with a trolley of mass 1.2 kilograms travelling in the same direction with a speed of 0.09 meters per second, so the initial conditions are the same as before. The heavier trolley has a speed of 0.33 meters per second after the collision. Find the speed of the lighter trolley after this collision. Well, again we use the conservation of linear momentum, so the momentum before equals the momentum after, and again we need to find the speed of object 2. So using the same rearrangement as before, putting in the new values gives a speed now of 0.63 meters per second. Is this collision elastic or inelastic? Well, again, if elastic, the kinetic energy is conserved, so we'll find that the kinetic energy before equals the kinetic energy after. The kinetic energy before is the same as the previous case at 0.44 joules. The kinetic energy after the collision is 0.37 joules, a loss of kinetic energy even though momentum was conserved. So this collision is inelastic.